Let's touch on finite differencing and spectral representation again. We've done that a little bit in Tom Stoker's book. So let's say we are looking at a pressure gradient in the x direction, and the finite differencing basically splits the distance or the domain into some grid points delta x. So at any I, x I is given by I delta x if x is 0 at I equal to 0. So here is the slope dp dx, and this is the pressure gradient dp dx at point xi is approximated by the slope of the line between two adjacent points. So we saw various representations of such gradients. So here is a grid point, here is a grid point, and we want to compute dp dx at pxi. Then you can write it as forward difference, backward difference, central difference, and gives you different orders of accuracy based on our Taylor series expansions, as you remember. So I'm not going to go back to that, but you can see the kind of errors you make when you do that discretization. Obviously, if you increase the number of grid points, you get much better accuracy, because your xi minus 1 and xi plus 1 will be much closer, as opposed to this case where the distance is so large that you are making some errors that are so obvious. So that's always a price you pay for coarse resolution. Of course, coarse resolution allows you to reduce computational times significantly as well, as we saw. So those are the things to remember. So dp dx, then written as a central difference approximation, is a pi plus 1 minus pi minus 1 over 2 delta x, and then you have second order terms here that are ignored. So this is a second order accurate representation of the pressure gradient. In a spectral representation, basically we write p at every x as some constant plus some sum over cosine and sine functions, which depend on wave numbers and wave length. Could be just the domain length. So in a global model, L could be 360 degrees or whatever the circumference at that latitude. So the number of zero crossings or number of maxima you allow from k equal to 1 to k determine the waves that you use to fit in the same slope. Okay, so instead of drawing a line, the spectral function representation gives you sines and cosines, so that dp dx can be then written in terms of the derivatives of these cosine and sine functions. So this is independent of x, so that drops out. This gives you 2 pi over L sum k equal to 1 to k times k bk cosine 2 pi kx over L minus ak sine 2 pi kx over L. K is here, you can think of it as zonal wave number of zero crossings or maxima that the spectral representation allows. So essentially that is your equivalent of the resolution in the x direction, truncation, as we talked about before. So larger the k, higher the number of waves you are allowing. So that's a slightly different way to think about, and there are advantages and disadvantages to each. As we talked about, for example, representing Coriolis can be an issue in a spectral model, and in the ocean model we almost never use spectral models other than in some coastal models and estuarine models and so on, where the geometry is very complicated and so on. So example of a spectral representation of a pressure field as a function of distance x and of the spectral pressure gradient at one of the points. The spectral representation is shown for 3 different truncations: k equal to 1, k equal to 2, and k equal to 3. Pressure gradient dp dx is shown only for k equal to 3. So you can see here our original dp dx and the slope we want to represent is here. So k equal to 1 with x over L in this space allows one maximum, whereas k equal to 2 allows one minima, maxima, minima, and k equal to 3 for k equal to 3, dp dx is shown here. These are p's and these are this is dp dx. So you can see that the accuracy of dp dx is quite good when you have k equal to 3. So that's the advantage of using the spectral representation, that some things work much better because Earth is a sphere. It's easier to represent it in zonal and meridional wave numbers, and even in the vertical you can do that, and that's also can be more consistent with the physics as opposed to the XYZ grid or the finite difference representation. So that's kind of very simple way of describing it. I'm not going into the details here, but you can also see how numerical solutions depend on the time step we use. We talked about the CFL Courant-Frederick-Levy condition for advection equation and said we described how numerical instabilities can be generated when you violate some conditions. So numerical solutions to a simple exponential decay equation is used here. Simple time stepping scheme and 3 choices of time step are shown. Dots indicate times for which the solution is computed. The case for the smallest time step is sufficiently accurate that it appears to overlie the true solution. The largest time step is slightly larger than the numerical stability criterion, so the solution erroneously increases with time. So you are starting with time t0 value known, initial condition, delta t or tau here of the decay time tau is 0.1, so the time step is fine. Then you can see that the solution essentially follows, the numerical integration essentially follows the analytic solution. In this simple case, the analytic solution is known. When you increase the time step to 0.5, delta t or tau 0.5, you can see the error grows, so you converge after some time, but you have introduced error. But when you increase delta t or tau to 2.1, you have gone beyond the numerical stability of the integration numerics, and you end up with false minima and false maxima, so you have a solution that is basically very far away from the analytic solution. So this is kind of the numerical error that we talked about before. There are various forms of it, of course. When we used leapfrog scheme, for example, we saw that the adjacent points get decoupled and you end up having massive numerical mode being generated. We also saw numerical dispersion, numerical diffusion, and so on. So this is just reinforcing some of the points. This is a schematic example of a vertical mixing for specific humidity Q and of the surface flux of moisture by evaporation, showing the processes to be parameterized on a grid with K levels. Moisture at each level is denoted by QK. Net flux across the face of the grid box at level zk minus half, that in reality would occur by smaller scale motions acting on the gradient in Q, must be parameterized in numerical models. So you have here the domain where the surface grid box is picking up the moisture, and those are fixed law exchanges happening at the surface, but the models don't represent it explicitly. They use a bulk formula that we saw before, where the evaporation depends on an exchange coefficient, wind speed, saturation humidity, air humidity, and so on. So that kind of bulk formula is used to pick up the moisture and advect it around. And then when you look at other grid boxes, let's say between level K and K minus 1, where the higher Q here in the lower grid box and lower Q in the upper box, because you are going up in the atmosphere, and there is a large scale flow, let's say, which is advecting things around, and there is exchange between the two grid boxes where the net flux is happening at K minus half here. So K and K minus 1 are here, so volume quantities are carried, let's say, in the middle. So you have QK here, QK minus 1 here, and zk minus half plus qk is exchanged by small scale turbulent processes, and those are represented in the model via parameterizations, because those are kind of the eddy covariances that we talked about. Just to make it easier, let me stop here and come back to sea ice and land processes in the next podcast. Okay, so we are adding just a little bit more details here compared to Tom Stoker's book, so I thought it would be useful to have these added at the end. So I hope you find them useful as well.